Florida is the second largest producing state of bell pepper in the US, with approximately 7,520 acres. Protective structures, such as greenhouse, high tunnels, and shade houses, are mostly used to improve fruit quality and yield, while protecting the crop against rain, wind, and freezing events. Nevertheless, these structures require relative high initial investment in comparison with open field production, making profits highly dependable on yield per unit area. Greenhouses require a high investment from growers, and in order to obtain the highest possible year net return, structure, irrigation, and fertilization have to work in harmony to exploit the genetic potential of the crop, while being efficient and economically viable. Water is a key factor for plant growth, needed in almost all developmental processes of the plant, from heat diffusion to plant support and photosynthesis. Knowledge of an adequate water management procedure in combination with sufficient fertilization will assure growers a good head start in greenhouse production. The objective of this project is to develop a low-cost irrigation system and guidelines for its use for 1 acre of greenhouse production of bell pepper. For this example, the greenhouse will be located at the GCRC at Bond. The soil type at the research station is classified as a Mayaca fine sand with less than 1.5% of organic matter and 6.6 of pH. Characteristics of the soil include approximately 38% of porosity, between 1.5 and 1.8 of bulk density, and 0.08 inches of water holding capacity at field capacity, and 0.04 inches at wilting point. Root depth for the crop will be considered to be 48 inches, however this will change depending on the crop stage. Red indeterminate bell pepper Alegria will be used for this demonstration. Plants will be germinated for 32 days in a small greenhouse where the temperature and light intensity will be controlled. Bell pepper growth is described by 4 stages in Table 1. KCs will be dependable on the crop stage and location. Here are the crop coefficients for bell pepper in the state of Florida, going from 0.86 at the beginning of the stage to 1.28 at the end of the season. The first step will be to decide the most adequate method for irrigation. Due to the plastic cover on top of the crop, ET values registered by phone will be considered not applicable. It is expected that the presence of the cover will affect the temperature, relative humidity, and wind speed perceived by the crop. Instead, the total amount of water to be applied will be calculated daily using the soil water holding capacity at field capacity and tensiometers as a water status tool at the field. Now we first have to determine the relation between soil water potential and soil water content. According to the soil characteristics, the field capacity is 0.08 inches of water, meaning that the amount of water per irrigation cycle should not be more than 0.08 inches of water per acre. The soil water potential curve provided by Brady and Whale in 2002 for soils with sandy texture is expressed in cubic meters over cubic meters of water, which can be also expressed as a percentage of water in a cubic meter and converted to liters. For example, at 0 kilopascals of pressure, the amount of water that the soil will hold will be around 0.25 cubic meters over cubic meters, or 250 liters, because a cubic meter of water is equal to 1,000 liters. If we translate this to an acre basis, this equals 6,605 gallons per acre in 1 inch at 0 kilopascals or 0 centibars, which is the unit used in tensiometers. If the root of the crop have a depth of 12 inches, then this final number will be 79,260 gallons per acre. So back to the 0.8 inches of water for field capacity, this is translated to 2,172 gallons per acre, or 26,000 gallons in 12 inches of soil, which is approximately 0.8 cubic meters over cubic meters at the soil water potential curve, which at the same time is related to minus 10 centibars of pressure. This will be a good indicator for the content of water in the soil for the daily measurements. Same way, wilting point at the soil is 0.04 inches of water per acre, which translates to approximately 1,086 gallons of water in 1 inch of soil, or 13,000 gallons in 12 inches. At the same time, that equals minus 100 centibars of water potential. In order to obtain a good crop, we should never get to the wilting point of the soil. So for this exercise, we will set as irrigation starting point at 75% of field capacity or 0.6 inches of water, equal to 60 centibars of pressure, and the irrigation will stop at 10 centibars of pressure or 0.8 inches of water in the soil. Tensiometers usually take some time to adjust to the changes in the water status of the soil. However, because we know the amount of gallons per acre needed to reestablish the field capacity, we will irrigate according to the gallons needed to get to 26,000 gallons per acre. After establishing the starting and ending point of the irrigation, it's necessary to establish how long the irrigation cycles will be. For this example, we will assume that the water flow for the meters is going to be 0.6 gallons per hour, and the meters will be spaced at 12 inches in double rows. Crop rows will be 4 feet apart, giving us 10,890 feet of row and 21,780 feet of drip-tape and emitters. If every emitter has a flow of 0.6 gallons per hour, it means that for 21,780 emitters, we will have approximately 13,071 gallons of water in 1 hour per acre, or 217 gallons per minute. This means that each irrigation will need to last approximately 33 minutes. Irrigation will provide back to the soil 0.04 inches of water per hour, or 0.02 inches per irrigation. Drip lines in this case will be auto-compensated and with anti-drain emitters. In order to schedule the irrigation of the greenhouse for 1 month, we will have to assume some parameters. For example, the number of times that the tensiometer will reach 75% of the field capacity in a specific crop stage. Assuming that the tensiometer will reach 60 centibars twice a day, that will mean that we will need 2 irrigations per day of approximately 33 minutes each. An example of this schedule is presented in Table 2. Water for the irrigation of the greenhouse will come from underground water and also rainfall, and will all be collected in a reservoir of 66 by 33 by 16.5 feet, which equals 35,937 cubic feet, or 267,730 gallons. 1 acre of greenhouse will collect approximately 27,154 gallons of water for every inch of rainfall per sieve. Water will be pumped from the water reservoir to the irrigation house, where water will go through sand filters to remove big particles and then to ring filters for smaller particles. Irrigation will have to turn on manually due to the nature of the irrigation tool to determine the water content on the soil, in this case the tensiometer. Pressure valves will be needed after and before the filters and after the fertilization system. Water and fertilizer will be pumped to the greenhouse at the same time. For the injection of the fertilizer, a fertilizer injector pump, or commonly known by its brand Dosatron, will be used. 4 pumps will be used at an injection rate of 1 to 100 for constant injection of the fertilizer. Fertilizer will be separated in 5 tanks, 1 for nitrates, 1 for sulfates, 1 for phosphates, 1 for micronutrients, and 1 for an acid solution for pH corrections. A check valve will be placed before the solution stock leaves the irrigation house to avoid backflow of water. In summary, the development of an irrigation system is a complex process where every detail from the crop, soil, environment, and implements available play an important role. This irrigation system might need a lot of labor for its function, but at the same time provides an affordable option for a greenhouse design for vegetable production. Tensiometers cost goes from $60 to $100, while weather stations capable of calculating ET goes from $700 to almost $4,000 depending on the equipment. Knowledge of irrigation basics can help growers save money and water while still get acceptable yields.